We're going to find relative extremas right here using the second derivative test. Now, in order to find relative extremas, if something's a relative max or min, we can use the first derivative test or the second derivative test. What's nice about the second derivative test, let me give you a graph to show you why it's useful. When we look at this graph, all right, if you look at critical numbers, you understand this right here is a critical number, this right here is a critical number. Now, at that critical number, what's your concavity? Well, isn't it concave down? So isn't it a negative concavity at that point? So at any critical number, if you're concave down, wouldn't that mean it's relative max? At any critical number, if it's concave up, wouldn't that mean your relative min? Yes. The second derivative test basically says at your critical numbers, if your concavity is down, it's a relative max. If your concavity is up, it's a relative min. Here's what it's saying. If you take your first derivative at c equal to 0, which is a critical number, okay, basically critical numbers, and if the second derivative at that value exists, then f of c, the coordinate, is a relative, this point, the critical number, is a relative min when the second derivative is positive. Okay, just like I said here, if the second derivative is positive, isn't that a relative min? If the second derivative is negative, like this, concave down at that point, isn't it a relative max? If the second derivative goes 0, you have to go to the first derivative test. The second derivative test does not work. So keep that in mind. It's not always work, but it is kind of nice. The second derivative test has its perks at times, so it's worth knowing. So let's find the relative extremas of this trig function on this interval using the second derivative test. All right, so what we're going to do is first find critical numbers, or find where the first derivative equals 0. So let's take the first derivative, f prime x is equal to, okay, that's going to leave a 3 out front. We're going to hopefully see chain rule here. The derivative of sine is cosine. We're going to leave the 2x. Okay, now we derive the inside, which is 2. Derivative of 2x is 2, so we now derive by 2. Okay, multiply by. And the derivative of 1 is 0, so that's done. That's easy, it drops out. So there's my first derivative. All right. After this, you are now going to find your critical numbers. All right. Now, you are also going to want your second derivative. All right. So let's find our second derivative later on. But for now, I want to set this equal to 0. So I set this equal to 0. 2 times this is 6. And I get cosine 2x. All right. I want to solve this. So basically, the 6 is not necessary. I can divide both sides by 6, ignore it. So I want to know, when does cosine 2x equals 0? Now, the 2x is going to confuse you, and I teach my students this little trick here. Hopefully, you like it. If not, you can use your other method you might know. But I want to know, instead of when cosine 2x equals 0, I want to know when cosine u equals 0. Instead of saying when cosine 2x equals 0, I'm going to say when cosine u equals 0. I'm going to try to find out when that is. And what I'm going to do is, what I did is u is equal to 2x. Okay, I replaced 2x with u, which if I divide by 2, you'll see why x is equal to u over 2. You'll see why in a second. But basically, I replaced the 2x with a u, something easier. Because for me, if I use my unit circle, when is cosine equal to 0 on a unit circle on this interval? Well, u is going to be what values? Well, think about the unit circle. Where is cosine 0? Well, wouldn't that be at pi over 2? And then next it would be 3 pi over 2. And then if you keep going, it would be what? It keeps going and going and going. So wouldn't it then be what? 1 more pi, so it would be 5 pi over 2, and then just keeps going. All right. So are these my values? No, those are my u values, but I want x. So if I want x, when I divided the 2 over, don't I basically have to take my u values and half them to find x. So what x is going to be, which that's what we're looking for, right? Aren't we trying to find x, by the way? Cosine 2x equals 0. You find x, but I replace it with a u. So aren't I to find x, don't I have to take each u and divide by 2? So what's this divided by 2? Well, it's pi over 4. What's this divided by 2? Well, it's 3 pi over 4. And could I keep going? But wait, I'm from 0 to pi. Actually, I don't have to worry about it. I don't have to keep going, because if I take the next one, it's going to be outside of this interval. So these are my critical numbers, or the values that I pay attention to see if they're relative maxes and mins. That's where my slope is 0 at these 2 points on this interval of this function. All right, so we got that. Now what we're going to do is we are going to take the second derivative finally. So let's take the second derivative of this function. Okay, I simplified it, so I'm going to use this function to take the second derivative. So I have 6 out front, and the derivative of cosine is negative sine, leave the 2x, and then derivative of 2x is 2. So my second derivative is 2 times 6 times negative 1 is negative 12 sine 2x. So that right there is my second derivative. All right. These are my critical numbers, my possible relative maxes and mins. And so what I want to do now is I want to use my second derivative, because at those values where the slope is 0, I want to see is it concave up or concave down. So I go to the second derivative, and what I'm going to simply do now is plug in, all right, into my second derivative. I'm going to plug my 2 values. So let's plug it into the second derivative, which is right here. So it'll be negative 12 times sine 2 times pi over 4. And what do you get? What do you get? Well, this becomes what? Doesn't that become pi over 2? What's sine pi over 2? Sine pi over 2. Sine pi over 2. What is that? Well, isn't it 1? So won't that be negative 12 times 1, which is negative? Doesn't that mean it's concave down? If it's concave down, what does that say about that point? Isn't this going to be a relative max? All right. Let's now do the other value. Okay, the second derivative of 3 pi over 4 equals negative 12 times sine 2 times 3 pi over 4. All these parentheses. Whoa, how many parentheses do I need? Okay, one more. Get that guy. All right. Won't that become 6 pi over 4, which becomes 6 pi, or cancel? Won't that become 3 pi over 2? What's sine 3 pi over 2? Sine 3 pi over 2 is what? It's actually negative 1. So what's negative 12 times negative 1? Isn't that positive? Which wouldn't that mean it's concave up? Which wouldn't that mean that at this value it's a relative min? Okay. So I have a relative max here and a relative min here. Let's find the coordinates now. All right. So we have to find the coordinates. So we go back to f, go back to the original function, f of pi over 4. We want to find the coordinates, equals 3 sine 2 times pi over 4. And what does that equal? Well, plus 1. I almost forgot the plus 1. It's so easy to miss little things, isn't it? and we put pi over 4 in, that becomes pi over 2. Sine pi over 2 is 1. Okay, so 3 times 1 plus 1 equals 4. So my coordinate is pi over 4, comma 4. And that is a relative, what do we say? Max. There is my relative max. Okay, now let's find f of 3 pi over 4. So that's 3 times sine, okay, and that would be 2 times 3 pi over 4 plus 1, don't forget that plus 1, and this becomes 3 pi over 2, which is negative 1, so I have 3 times negative 1, which is negative 3, negative 3 plus 1 is negative 2. So what I have now is 3 pi over 4, comma, negative 2 is a what? Is a relative min. Now, why do I again know it's relative min? Well, a relative min because it is concave up at that point. So, what I did, let's go back through. To use the second derivative test to find relative maxes and mins, you first find the first derivative, find out where e equals 0. Okay, those are the two values. Be careful, I replaced 2x with a u in this particular problem because I thought it'd be easier for me, and I converted the u's back to x's. Then, once you got these, then you take your second derivative, which is fairly easy, and from there you plug in these two values into your second derivative, and you look to see if they're positive or negative. Negatives mean it's concave down, which means it's going to be a max. Concave ups are going to be mins. And then once you know what the relative maxes or relative mins, then you find the coordinate. So you plug it into the original function. A lot of people plug it into the wrong functions. They go back and plug it in this one or something. Don't do that. But we plug it into the original function, and then we got the coordinates of the relative max and relative mins of this graph on this interval. Now, here's an application of it. Let's look at this. All right, watch this. An application. The profit made by a store on a busy day follows the function BAM. The store will be open for 10 hours that day. Let T represent how many hours it has been open so far, and P is the profit. When was the profit most and least profit? When was the most profit and least profit? So, if I want most and least profit, isn't that a relative max, relative min? Okay. And if I have this graph, and I didn't have a graphing calculator to graph it, well, what you would do is you take the first derivative of this, find out where e equals 0, got these two values, then don't you take your second derivative, plug in 3, plug in 9, found out that's negative, so concave down, this one's concave up, so wouldn't at 9 be a relative min, and at 3 be a relative max? And if I wanted to know how much profit, well, at 3 I got 36, and at 9 I got no money. That's not very good. That's why you had the least profit, no money. So, what does second derivative test do? It gives you the ability to solve regular problems, because in life, if you want to know the most profit from a given scenario that you can depict with a graph, absolute maxes and mins or relative maxes and mins are very important in real life, okay? Especially with businesses, especially with profit and money. We want to know when our best and worst times are. That's important. Now, this is also an absolute max problem sometimes because you could think of 0 hours or 10 hours, but I kept this as a relative max and min extreme up problem. So it's just showing an application of why we want second derivative tests. Even first derivative tests would have worked. It would have taken longer because you'd have to make your intervals and everything to see which is your relative max and relative min. So hope that helps.